This is a tutorial on identification of the dominant mode of instability around a tunnel. And it's an important theme in this course to identify the dominant mode of instability because it affects what kind of tools we're going to use to evaluate stability. And it has a big impact on what kind of ground supports are going to be most effective in different ground conditions. We're going to use this chart from Kaiser et al. 2000. This is the one I prefer to use. So here's the problem. You're working on a tunnel through a mountain region. The horizontal stresses are estimated to be twice the vertical stresses. The average unit weight of the rock is assumed to be 25 kilonewton per cubic meter. And based on a preliminary site characterization data, the table below has been compiled to summarize the expected conditions for each segment of the tunnel. Determine the anticipated dominant mode of instability for each segment. Okay, so we're going to look at these four different tunnel segments here. TS2, 5, 12, and 16. And they're in different changes or distances along the tunnel alignment. And we have a design depth provided for each of the tunnel segments, ranging from 115 meters to 1,325 meters below the ground surface. We're going to be looking at four different rock types: limestone, schist, granite, and shale. And we have the UCS value here, or sigma C, for each of these rock types. And we have an RMR to classify the quality of the rock in each segment, and also a little description of the jointing to give us some preliminary assessment. So right off the bat, what do we see? Well, limestone here with a very competent unconfined compressive strength and pretty good quality rock with 3 joint sets. Okay, and probably, given that it's limestone, one of them is probably some kind of anisotropic structure. And this is fairly shallow depth. And then we have a schist, which is a metamorphic rock that has some kind of schistosity structure, which is anisotropic as well. It's fairly strong, and it also has a pretty decent RMR classification. And we're talking about a granite, which is very strong and probably brittle. It is of high quality, right, with few joints, right, but is quite deep. So that's going to imply pretty good tunneling conditions, but if the stresses are high enough, we could have some problems with brittle failure. And the shale is quite weak, very weak, 12.5 MPa, extremely low RMR, but look at this, it has few joints. So really the RMR, the jointing and structure and fracturing doesn't seem like it's responsible for making this very low RMR. It's primarily the strength. So what we're talking about is probably a fairly massive but very weak rock, which will have its own unique type of failure mode. So we got some idea of what to expect right out of the gate. And we're going to be using, again, this chart by Kaiser et al. That I really like here, where we have the maximum stress over the UCS. You'll notice on this particular chart it's called sigma UCS, but we like to use sigma C. And so that gives us some ratio of the strength of the intact rock to the in situ stress field. And across the top we have the RMR, and this gives us a matrix of different kinds of tunnel behaviors. Okay, so what do we need, right? We have RMR, okay? we need to figure out sigma max so that we can start to identify what region each of these will fall into. Okay. So, you know, it's a fairly tedious calculation, but it's straightforward and can be automated into Excel or any other computer. I'm just going to do the calculation by hand for tunnel segment 2, which is in limestone, and the rest will be very similar, and then we'll talk about what we got all together. So for tunnel segment 2, we have RMR of 65. We have a sigma C of 105 MPa. We have a unit weight of 25 kilonewton per meter cubed, and we're assuming that's for all the overlying rock. We are at a depth of 115 meters, design depth, and our horizontal stress ratio is 2, okay, which, just in case you don't remember, is the horizontal stress over the vertical stress. All right, so that's what we're going to use to get our stress field so that we can figure out the maximum stress. All right, so just as a reminder that sigma max is essentially comes from Kirsch solutions simplified and gives us the maximum stress that we can expect tangentially around an opening. So if we have a circular opening, okay, we'll have a sigma max. In this case, the maximum stress, K is 2, is horizontal, right? That's going to be the maximum stress. And so sigma max is actually going to occur right here, okay? In the crown and in the invert, right? So that's going to be our maximum tangential stress. And the equation for that is 3 times sigma 1 minus sigma 3, okay? And in this stress field, sigma 1, the maximum principal stress, is going to be our horizontal stress, right? And sigma 3 is going to be our vertical stress. So we need our vertical and horizontal stresses, essentially. Okay. So let's start off and calculate the vertical stress is equal to gamma Z is equal to 25 times 115 meters, okay? And we're going to divide that by 1,000 to go from kilonewtons into meganewtons so that our answer is in MPa. So that gives us 2.9 MPa. Okay, so that's SV, which is also our sigma 3 value. SH is going to be equal to K times SV. Okay, so we're going to have 2 times 2.9 is 5.8 MPa. And that is our value of sigma 1. From that, we can calculate sigma max. Okay, is 3 times sigma 1 minus sigma 3, 3 times 5.8 minus 2.9, and that's going to give us a value of 14.4 MPa. right? So sigma max is 14.4 MPa. For TS2, right, under these conditions, and again, it's just assuming perfectly elastic behavior around a circle. Okay? Even though our tunnel is, might be a horseshoe shaped, it might be another shape, and it might have plasticity, but this is the calculation we come up with to come up with a sort of an estimate of the maximum stress under simplified conditions so that we can compare it with the strength and use it in our mode of failure chart. All right. So what do we really want to know? Okay, so that we can move ahead with our assessment of mode of failure. Okay, we are going to want to know sigma max over sigma c. 14.4 MPa divided by 105 MPa is going to give us 0.14. Okay? So, mode of failure. Or instability, okay, is going to be based on RMR of 65, okay, and sigma max over sigma c of 0.14, right? So we're going to go over to our table here, or matrix, okay, and for RMR of 65, we're going to be in the center column, okay? RMR is between 50 and 75. And it's worth noting that we're pretty much right in the center of that, right? We're not right on the edge, okay? That's something you have to be wary of if you're transitioning from one mode to another. You have to pay attention to that, and the same with the stresses, okay? And then when we have a sigma max over sigma c of 0.14, okay, that's pretty low, okay? And so up here, you can see that the top row is when the ratio is less than 0.4 or so. So we are in that region right there, okay? And so we're pretty much somewhere smack dab in the middle, maybe in the upper part. And in that case, we have a low stress environment with a sort of blocky ground, and we can anticipate falling or sliding of blocks and wedges. Okay? So falling or sliding of blocks or wedges. That is the anticipated dominant mode of instability for this case. Okay, so I went ahead and used the computer to calculate the same information for all the other tunnel segments, and I'll just summarize that here. Okay, so we got the segment, okay, rock type, RMR, and our stress ratio of sigma max over sigma c. So we have tunnel segment 2, tunnel segment 5, tunnel segment 12, and tunnel segment 16. And we were talking about limestone, schist, granite, and shale. And the RMR bars were 65, 58, 84, and 37. And then with the computer, we calculated the stress ratio of 0.14, as I showed you above, 0.66, 0.90, and 1.3. Okay. All right. And just off the top of my head, usually when you get up handy a stress ratio of 1, right, that means the stresses are approaching the unconfined compressive strength of the rock. That's a good indicator that you're getting some real stress-related problems. So I plotted these using the computer, again, over here on the right, the different tunnel segments, and I listed them by rock type here, you can see. And then we can compare this plot here to the matrix on the left, and you can see the dividing lines in the grid to help us see what kind of conditions we're having. And so you can see the limestone was in the top center right here with falling or sliding blocks and wedges, right? So a structurally controlled situation. The schist was a similar RMR, but under higher stresses. We were going deeper under the mountain, and so maybe a little bit less wedge instability because there's a little bit more clamping, but there's starting to be some stress-induced failure. So some localized brittle failure of the intact rock and some movement of the blocks. So that's the sort of thing we're anticipating here. Okay, the next one is the granite, right? It had a really high RMR. It had few joints. It's very strong and brittle, and it's fairly deep and under a lot of stress. And that stress ratio was really high. It was 0.9, right? Getting up there to 1. So, you know, really we're talking about some brittle failure adjacent to the excavation boundary, but, you know, it doesn't seem like it's going to be under extreme stresses, so it's a pretty decent tunneling condition. And then we have the shale, right? So it was fairly unjointed, although it probably has an anisotropic bedding structure, but it is very weak, right? And so the stress ratio was really high, 1.3. And that's putting us into a sort of it's indicating a squeezing and swelling type of condition. And, you know, it plots very well there. And that's, you know, our assessment of the anticipated dominant mode of instability is consistent with sort of our description of the conditions there. Okay, so now we have a pretty good understanding of the anticipated dominant modes of instability, and that's going to affect how we're going to conduct analyses and what kind of ground support is going to work for these different cases. For instance, the limestone with the wedges, right? We're going to do like a limit equilibrium analysis. We're going to do structural analysis with stereo nets. We're going to do some probably going to reinforce that with some rock bolts, right, to try and reduce sliding of wedges and falling of wedges. Schist is going to be, you know, fairly similar to the limestone, but there might be some brittle failure and so on that might affect the type of rock bolts, or the shotcrete might become more important than it was in the limestone, where it wouldn't probably be as effective. And then we go into the granite. Okay, you know, in some cases we might expect some brittle failure, but overall a fairly good quality rock in, you know, not overly high stresses. So that might require some kind of, you know, energy absorptive ground support. and certainly some mesh. And the shale, well, we're going to experience some squeezing in that condition, and maybe some swelling and that sort of thing. And so, simple plasticity solutions work very well for that. But perhaps swelling needs to be accounted for in some other way. It's not easy to analyze that very simply. And the ground support in that case, we want to have something that's able to accommodate large displacements but still stabilize the excavation. So those are the kinds of things we are going to have to keep in mind. And that is why it is so important to understand the anticipated dominant mode of instability.